Thanks all for coming. I'm Craig Blitz. I'm Senior Product Director and Product Manager of Lightbend's Fast Data Platform. And I'll be talking about some technology that we're working on called pipelines, along with Gerard Maas, who's one of our senior developers at Lightbend. And Gerard is going to give a demo after I give some introductory slides. And just as a reminder, this is technology that's not yet released, so we're speaking about roadmap, and of course roadmaps are subject to change, both content and timeframes. So want to set the stage by talking about what a streaming application is. We talk about streaming data or fast data quite frequently without taking a step back and thinking about what we mean, because I think when different people talk about it, they mean different things. When we talk about fast data applications, we have a big focus on that last word, application. That is, we're building applications that are then being infused with streaming analytics or with model serving, but they have all of the same requirements that any application has. They have to be scalable, they have to be resilient, they have to be always available. And one other thing that we frequently forget, they have to be agile. You have to be able to introduce new functionality fairly easily, and you need to be able to rev these in production, right? So you need to think about all of this stuff. I've listed some typical use cases on it, loan approval, IoT predicting device failure, very familiar use cases. And then importantly, you want to mix, because they're applications, you want to be able to mix your domain logic with streaming analytics, with model serving. But you need to be able to incorporate domain logic into your applications. Just a quick show of hands. How many of you have heard of the Lightbend Fast Data Platform? Okay, most of you, great. So Lightbend introduced the Fast Data Platform last year as a platform that supports you building and running these fast data applications. The way we think about it is that we've extended Lightbend's fast data reactive platform. We've extended the ability for you to build reactive microservices-based applications, and added the ability to run streaming engines, serve models, et cetera, and wrap that all with our Lightbend console with Enterprise Suite to allow you to do management and monitoring, and provided what we call FDP Manager, Fast Data Platform Manager, which is a central place to manage your fast data components. What you don't see in this picture is anything, let's say, above the top that's kind of aiding the developer and the DevOps person to orchestrate all of these components, right? These components are exposed to you fairly raw. So you write Akka Streams code, you write Spark code, you figure out how to wire them all together. There's nothing really helping you to do that job in this picture. And that's kind of what we want to start to address, right? At the same time, extending the box with management and monitoring, extending it to include this new functionality. And this new functionality is what we're calling pipelines. All right, so Akka is our tech lead for pipelines and helped formulate the vision for what we're trying to do. And very simply said, what we'd like to do with pipelines is to enable you to run multi-component, multi-stage stream processing systems, expose those stream processing pipelines as microservices, both on the ingest side and on the outbound side, and to be able to assist in the development of that. I'll show you how we remove boilerplate, and assist in deploying and managing those pipelines. So before we begin, I want to think about the different personas that might interact with this type of platform. So we typically talk about your app developer. Those are the ones building your microservices-based applications. Your data engineer, who is used to working alongside of a data scientist, trying to figure out how to aid the data scientist. And then finally, of course, the data scientist that's building your models. So if you think about the challenge of fast data applications from an application developer point of view, they're faced with the new challenge of how do I bring in intelligence? How do I bring in AI into my applications? How do I, sticking with an earlier example, how do I take my auto loan application, auto loan application, is that the word? So I'm applying for an auto loan. Now I want to infuse that application with the ability to make a real-time decision on whether I should approve that application or not. How do I do that? How do I tap into the expertise of my data scientists and my data engineers and expose that to the application? The data scientist faces a similar challenge that they've been asked, for a long time, they've been focused in the world of big data about looking for business insights to help improve the business. Now they're being asked, how can I take the results of my work and think about how it might work in real time? How can I export those models? And then the data engineer is responsible for how do I turn those data scientists' ideas, how do I turn those pipelines into something that could be scalable, et cetera, meet the real-time needs of the application. And who did I forget? Probably forgot a few people. But one key person that or one key persona I forgot is DevOps. How do I turn this big pile of goo into something that I can manage? Right, something that I can deploy, something that I can upgrade, et cetera. So why fast data pipelines? Why are we doing this? Well, for one, we want to be able to manage and compose applications that comprise lots of moving parts. We want to be able to evolve those applications. These applications aren't static. Schema changes, requirements change. Even just during the development cycle, you want to be able to rapidly upgrade your application. We want to be able to serve models. And of course, we want to be able to expose pipelines, our streaming pipelines, in a way that's familiar to us in terms of managing applications, expose them as a service, as a microservice, and treat them as a microservice. They should be able to update them or upgrade them as easily as you upgrade a microservice. So here's a sample use case that kind of shows some of the complexity. This is actually just a POC use case. We built this as a POC. It's one of 4 very broad use cases that this company wants to do. And because it's just a POC, it represents just a small part of that one use case architecture. But already you can see the number of moving parts. And you can see how difficult this would be to manage independently. You have to manage your Kafka topics. You have to manage your serialization. There's nothing really here doing schema management. If you think about how you're going to evolve schema, you're kind of on your own, right? And all the deployment is manual, right? So we want to be able to help address this. And the the other thing that you see is that we did expose this as a microservice in the upper right, but of course all of that was hand-coded as well and hand-deployed. So why fast data pipelines? So fast data pipelines is intended to increase productivity, reduce your time to market, all the standard things. But the way it does that is by automating a lot of developer and DevOps tasks, by automating serialization, doing schema management, doing deployment for you, managing your Kafka and your Kafka topics that sit in between stages of your stream processing. And of course, deploying those pipelines, exposing them as microservices. So some concepts before we get into a demo. So we have a concept of a streamlet. A streamlet is just a processing element in your pipeline. And streamlets could be written in any of those streaming engines that we showed in the fast data pipeline architectural picture. Today we support streamlets in Akka streams and in Spark. There's no reason to not extend that to all the engines we support in fast data pipelines. Streamlets have different shapes, including ingresses, egresses, the ability to fan in, to fan out, to do joins, and apparently I have a typo there. Each streamlet, so streamlets have multiple inlets, multiple outlets. Each of those inlets and outlets have schema attached with it. So if you went to Colin's talk yesterday, he talked quite a bit about the ability to automatically figure out which schemas can be applied between one processing element and another. Something that we do. We have strongly typed schemas where we check at compile time. And then finally, we have the notion of a blueprint. A blueprint is just a file that represents how your streamlets are wired together. And a blueprint, so blueprints are edited locally, and then you can go and deploy them, target them to a cluster. So we simplify development. I think this is what some of the things I've talked about. We remove a lot of the boilerplate. I'll show you what that looks like in a sample Spark process. We allow you to wire things together in a blueprint. And then finally, via CLI and via UI that's under development, be able to issue a command to deploy that blueprint to whatever environment you want, to a test environment, to a production environment, et cetera. So this is what the code like. So without pipelines, this is some very simple processing code in Spark. And I say simple, although it's like 2 pages here. The interesting code is what's circled in the upper left there. This is what's processing your business logic. What is the rest doing? It's setting up serialization. It's configuring your Kafka topics. It's managing Spark itself. All of this is stuff that a developer shouldn't have to worry about and makes your code somewhat brittle, or really brittle if you have to manage a lot of these. With pipelines, this is what the code looks like. We've removed all of the boilerplate. You only have to provide your process function. So that's the developer aspect of how we simplify development. But then we also simplify deployment and operations by doing things such as orchestrating the deployment of your distributed application. So in the sample use case I showed, there were, maybe 15 moving parts. We'll orchestrate that deployment. provide centralized management via the LifeEnd console. I'll show you a quick screenshot of what that's going to look like. And then in the future, not there yet, but automate scaling, automate SLA management around these pipelines. So the workflow is very simple. Basically, you develop your processing functions, what we call Streamlets. You wire them together in a local file called a blueprint. You compile them, push Docker images that can then be deployed to the runtime via CLI or UI. And we run everything, same as Fast Data Platform, we run everything in Kubernetes. Then the next phase of it, and this I'll talk to very briefly, but the next phase is how do I integrate my domain logic into these pipelines? I want to be able to, I want to do several things when it comes to microservices. Of course, I want to be able to expose my streaming pipelines as microservices because they want to integrate nicely into a microservice environment. But I want to be able to embed domain logic into my streaming data pipelines as well. And so basically what we want to do is break down those boundaries between stream processing and microservices. When you hear a lot of people talk about stream processing, they talk about ingest, very fast ingest, into something to be processed later, into Hadoop or into some place where you're going to process that data again later. That's not what we're interested in. We're interested in serving this directly to a real-time application. And we want to allow for a very flexible deployment model. We want to allow stateful, stateless services or streaming data pipelines. Some buzzwords for you. Since this is the Reactive Summit, and we talk a lot about reactive microservices here, wanted to give you a little bit of an insight into how we're thinking about this problem. We're still very much in development with this phase of it, but we're thinking about how to expose event-sourced Lagom microservices, Akka-based microservices directly to the stream, so that your domain logic is sitting right there, and then via server-side events or server-sent events, or via SQL queries or projections, interacting directly with the streaming services downstream from it. And so you could think about entering your application via the microservice and then having that microservice generate events that get fed downstream, right? And this will be fleshed out over the next couple months, and we're very excited about how we're going to be able to combine the microservices world in general with the streaming data world. And with that, I want to turn it over to Gerard for the demo. And
right.
Hopefully I left you enough time.
Thanks, Craig. That's great setting the scene for the Pipelines project and what we can bring and deliver for you in order to create, build up, and publish fast data applications using pipelines. So Craig introduced this use case from one of our customer interactions, and it's composed, as he mentioned, of many different moving parts. But the important thing to realize here is those parts are flowing into each other. So there is a certain a concept of data coming in, data being processed through the system, and data going to some other places. So it comes in at the left side from some sources. In this case, are documents that are being pushed over a wire. They are then capture, that they enter the system. We call that an ingress, enter the system, and they are validated. There is a validation step there in the middle. And after the validation step is done, then we proceed to do some aggregations on it and produce the results somewhere else for further consumption. In this case, we are producing those results to Cassandra and to HDFS. I'm going to give a simplified version of it. Of course, I'm not going to implement all that in the 5 minutes that we have for this demonstration, but I want to highlight the different elements that Pipelines is bringing on the table to make the implementation of such a use case really fast, very efficient, and actually I would call a very interesting experience to take it from a concept to development to your final production system. We mentioned the different concepts in pipelines. We have what is called a streamlet. Streamlets could be inlets or outlets, or in this case, we call it ingress and egress. Those are the points where data enter the system and the points where data exit the system. In between, we can have other streamlets that are using different runtime environments. And we currently have Spark as a backend and Akka Streams as a backend. And we can combine those at our will. There is no restriction there. We can create the streamlets that are using the Spark backend for the things that Spark is doing really great, like, for example, aggregations, and like we're going to do there. And we can use Akka Streams for the same purpose, to use the right tool for their job. Let's jump now into code. I hope you're ready for some coding, because we have a lot of code here I want to get through. The first thing is I think I need to restructure this a little bit. Let me see, is it fairly visible? Yeah, all right. Let me close this down and give you a snapshot of how that looks like from maybe a higher level view. All right, so we have a project, and that project is composed of different sub-projects. We have the ingestion part in this implementation using Akka Streams and Scala. We have the aggregation output. We have a all-composing project that contains the blueprint and how all the pieces go together. We have the Spark aggregation, but we actually start by the data model. And that's very important. I think it was highlighted in yesterday's talk as well. When you start developing a pipeline and thinking about how your system behaves, you start by looking at the data that comes in. And once you look at the data, the first thing you're going to realize and want to fix is the schema of that data. And that we are enabling by providing you schema-first development experience. So we have here we're going to create what is the shape of a call record, and that's how the call records are looking like. And I have some sample data next to it, so that we can verify, okay, that's the data that's coming through the system. I got the sample, I capture the schema of it. Once I have the schema captured, then I can generate some schema definitions. From those schema definitions, we're going to generate the code that is going to fuel the different pieces of the application. I don't know how many of you have written some Spark applications? Okay, we have a few. Let's see what you find of the following way of doing things. Well, the first thing is an ingester. So we have a point where things enter the system, and this is all you need to do. You need to declare that there is an entry point, and that entry point has a given type. We are going to do the heavy lifting for you. We're going to take that schema. We're going to validate the data that is coming in. And next to that, we'll see a deployment time. We're also going to generate the ingress in Minikube or in Kubernetes to get the data into the system. What is behind that is a whole, so this is the top of the iceberg. And behind that, we have a very detailed implementation of how such a thing should look like. And it's done by the person who wrote the book about Akka. So you're getting here a lot of knowledge packaged in a very easy-to-use API. So we have that concept of streamlets. There is a library of streamlets. Those streamlets are enabled on your build file, by calling plugins. So I am saying here, this project is enabled with pipelines Akka Streams plugin. Once I do that, the API is loaded into your project. You can use the Streamlets that are provided by the library. And we also have the facility of saying, OK, this thing is going to be built into an image that can be deployed later on. The same thing for Spark. So for Spark, we also have a Spark plugin. And you can add any dependencies here. We are not constraining you on the libraries you can use. All we are saying here is that you have a project that is located there in the directory and has enabled the support for Spark. When we have this support enabled in Spark, let me give you, and it's below. Then we can develop a Spark Streamlets, or Sparklets, if you want to call them like that. And this will look like this. As Craig showed, we are focusing here on developing the business logic, all the management of Kafka connections, all the setting up of checkpointing and managing checkpointing, mounting up volumes, running this on Kubernetes. It's all done by the implementation behind the API. And on the API itself, you get access to the native API from Spark. So if you have an implementation today, then you can take snippets, copy-paste it into the context of this Sparklet and migrate your existing functionality. If you're starting developing streaming applications, then we are removing all the boundaries and all the threshold that you have around you of complexity and let you focus only on the business logic that you want to achieve. Once we have set up all our components, we think about developing this pipeline. It's about developing the pieces and then connecting those pieces together. Those pieces we connect together using a definition of a blueprint. A blueprint is also a file, and it's here. And we have a blueprint definition. The blueprint is written in a configuration format in Hokan. And what we're saying there is that we have a number of streamlets defined in our system. We have an ingress, we have a validator, we have an aggregator, and we have two different types of egress. One for the error records that we may find in the stream, and another one for the data that we process successfully, and we have an aggregate form of it. Then we proceed to connect those streamlets together. We connect the input, the ingress, where the data is coming in. We connect it to the validation part. That validation part will give them two different paths. One, the data that successfully passed the validation will proceed to the aggregation, and the data that fails validation, that is not following or requirements, it will go to maybe a dead letter queue, maybe a topic where you hold the data that needs to be checked later on. All this is checked at compile time. So once we have this developed, we can do something like verify compiles the whole project, and then checks that the connections between the different elements are matching, and that all the connections between them are fulfilled. Let's say, for example, that I want to connect the output of my validation errors, which is the out 0 that is reporting the errors. I wanted to connect to the input of my aggregation. So what I'm saying here is I want garbage in, and we don't want that, right? We don't want garbage going into the input of our system, of our aggregation system. So once we do verify, then we see a compile time error saying this cannot be done. The validation output is not compatible. Types are not compatible. And that's driven by the schemas that we defined up front. So we have a schema-driven definition of every step, and you can only connect those schemas that make sense. That prevents you from making mistakes and deploying things on your runtime system that are not going to work once you start the system as such. Once we have all this, and let me just put this back in place, there are two, I think that's it. There are two important steps to follow. The first one is to build and deploy this project. I'm not going to do this right now. It requires to run Docker and publish the Docker images to your running environment. It takes a little while, and I think we are not having that time right now. The other step, so that will be build and publish. That's the first step. Let's not do that right now. We do two things at that step. The first one is make a package of your definition. We have a blueprint that knows how all components are put together. And from that blueprint, then we're going to say, OK, this part is belonging to a given runtime. We're going to create a Docker image for that. Then we're going to create another Docker image for the other runtime, let's say one for Spark, one for Akka Streams. We're going to push that all to your backend. And finally, we're going to start the application. To start the application, we have a command line tool. A command line tool, very familiar to every one of us, and is also very friendly to your CI/CD environment. So if you want to automate all this, then you just need Jenkins to call this API. And the first thing we can do is, for example, listing the applications. I had already published that application, so it's available on my system. The next thing I want to do is to take that application and let's publish it. And it starts the application. We can say, instead of deploy, monitor the status. It goes very fast because right now, if I see the configuration of my system, I get confused between. So we are running a Minikube. Yeah, like that? All right. OK, so we have deployed the application. How is that application looking like? So let's have a look at it. And maybe let's have a look at it in another. All right. So we have then our application running on Minikube. There is a namespace created for the application. There are deployments, and the deployments are generated for you. I don't know who loves to write YAML, but I don't. The first time I tried to deploy an application myself, I think following all the components and all the pieces that you need to build your Docker image, to write the different deployments, to understand the deployment model for Kubernetes, that you need to have the replica sets, you need to have an ingress definition, you need to have services to be able to access your application. It takes a while. It took me, I think, probably more than 2 weeks to understand all the pieces and put them together. Now we did it in just 5 minutes. And each of these deployments contains a pod, and those pods are currently executing. And let's send some data to this thing. Now we have an application running. We can send it some data. And send data, and we're going to take these data samples that we have in the data model and start sending data to it. So we have an accept. We see let me just break it for a second to show you what's going on. So we, at deployment time, the ingress that we defined deployed also an HTTP endpoint that we can now access using this simple curl behind this. So we are just posting data to that system through that endpoint that's been deployed by the application. OK, so let's send a bit additional data. And now there is another very interesting there's another very interesting feature. I don't know how many of you have deployed their first streaming application, and the first question that pops to mind is this doing something? Because typically, streaming applications, they don't have a console. They are running on the back end. They are getting data in, processing data, and putting data out. So normally, the way you have to see that data is flowing through the system is picking at the output of that element. And we do this by checking out the output. For example, I have the output of my ingress here. It's declared in my blueprint. So I can say, okay, I'm going to say pipe tail, then the name of the application, and then the given endpoint. And there the data is there. So the data is flowing through the system, my producer is sending data, and the data is getting through it. This is the raw data. What about errors? Do I have errors? So let's have a look at the errors. This is my error output. And of course, we have some. I wouldn't show you this otherwise. We should have some. But those errors were at the beginning of the file. So if we start tailing the data from the moment we're receiving the data, we might have been missing something. So we have this seeking feature where you can see what happened there in the past and is still on our streaming backend. So we can say, let's follow, but let's follow starting some 100 messages ago instead of as from now. And there we have some of the initial data in that file. It was too old. And it's getting removed from the stream and put on a secondary, in a secondary flow for error management. All right, so this is kind of a tour of the application on how the developing with pipelines look like. There is one additional thing I would like to show, the proverbial one last thing. And that is that we have a definition of clusters. So we can say get clusters. And I always start get. Yeah. And sorry, this is the current one. And we have a Reactive Summit cluster deployed on Google Cloud. And we can then set that. Once I do this, I can do pipectl app deploy, and sorry, I need the name again. Oh. Yeah, typos chasing me. Let's call record pipeline. Deploy this. And this is in pending mode. This doesn't go as fast. We are deploying on the cloud right now. Sorry, status. And let's see. OK, so we have almost an application running there, except for the ingress that's pending, but it will come up in a second. And let's have a look here. Let's refresh this view. And we have there. We are running the same application we developed right now. Now it's running on Google Cloud, up and running. It has an external ingress that you can reach from the internet, secured for you. It's already published on the DNS names, and you can start interacting with this application right away. So we went from a local environment. Actually, we went from a concept. We went from the idea that we need to build up an application, then we break that application in logical steps that we want to compose together. We implement each one of those steps, and from there on, we help you to get this deployed first on your test environment, let's say Minikube if you're running your local system, or on a locally deployed in a cluster, and then take this to any cloud that is supporting Kubernetes. And of course, at some point in time, you want to decommission things. And so we can say remove. Sorry, on deploy, I always get it wrong. There we go. And now it started. If we go back to Google Cloud and we refresh this, then bye-bye, the application is gone. We have a full lifecycle management of your application through the whole development and deployment lifecycle. All right, with this, I think we are wrapping up. Just 4 takeaways for you. The applications are schema-driven. You focus on your business logic. You develop the pieces that are important for your application, for running your business, focusing on what is delivering you value. All the validations are run on a compile time. It saves you a lot of time of the testing cycle, and all this technology is cloud native. You run in Kubernetes, and every Kubernetes cluster you have, you can get your application up and running in minutes, as we just saw. Thank you. Craig, all yours.
Thank you, Gerard. Thank you, Gerard. I'm going to leave this slide up. You can get a preview of what our UI will look like. But since we're short on time, I'd like to invite anyone up to the microphone if you have questions.
What is your security model for, like the endpoints? Are they wide open, or can you say who can access them? Or
right now, the security model is based on credentials, and this is the first implementation that we have. And we have quite some knowledge internally on how to secure every component, and that will come down in the roadmap. So it's not implemented yet. Right now, just basic credentials are there for securing those endpoints, but they are not wide open.
Thank you for the great presentation and demo. I would like to ask about other platforms than Kubernetes. How about DCOS Mesosphere? Are you going to support that as well?
Yeah, so the answer is yes, but we will support it by running the components within Kubernetes on DCOS. All right, so today, part of the story that I didn't tell is the underlying fast data platform story. Fast data platform was released about a year ago on DCOS, running native DCOS frameworks, and we're evolving that to run on Kubernetes in line basically with where the industry is moving. Any other questions?
I saw your schemas were defined in Avro.
Yes.
Does it support other things like protobuf?
Not yet, but there is nothing stopping us except effort spending. So we are not saying that Avro is the only way. Avro is a current only implementation, or the model we are using behind it supports actually schema definitions. So it opens the door for definition of protobuf and any other.
Thanks.
Any other questions? All right, thank you all for coming.